Okay, let's go and get started today. This is class 5, and today we're going to start talking about proofs, and specifically about direct proof. And as a quick review, previously we'd looked at regular expressions, and those regular expressions essentially consisted of either one of the primitive ones or one of the composite ones. And we had these primitive ones, these composite ones. We've seen these before. You should be working on a lab, so you should be familiar with those. And then we had used those operators and those regular expressions and shown that there are properties of them, algebraic properties of them, just like there are with algebraic expressions, things like the associative properties and commutative properties and distributive properties. Same thing is true for regular expressions. And we came up with this set of, in our case, 15 of these algebraic properties that we were using. And we did that to prove equivalence. And so in this example we have here, is this thing on the left equal to that thing on the right? Is all of this equal to A star? Are those equivalent expressions, meaning do they define the same language? And we could go through and manipulate that and say, okay, well, this part on the left here, where these are all separated by the union operator or by the or, well, we could regroup those using rule 2. And when we regroup that, we've just moved the parentheses over around the plus and the lambda. We have a rule for that, which was 15. So by using 15, A plus or lambda is the same as A star. So now we have A star union A star. And anything union with itself, using rule 9, is the same as itself. So now we have A star star. And then using rule 10, we wind up with A star union A star is equal to A star. And then collapsing all of that up so you can see it better, use rule 9 there to have now A star union with A star is anything union with itself is still itself. Same rule we used up here. So A star is equal to A star. So yes, those two original expressions up all the way up here have now been shown to be equivalent because we have used legitimate rules, algebraic properties of those regular expressions to justify each step to manipulate them so now they match each other. Now let's look at one more. So here we have A plus is equal to that whole thing on the right. And to do that, we're going to manipulate the right. So we start with that. We use rule 2 to get this. In other words, we've just redistributed just like we did in the last one. And now we have A plus or lambda using rule 15. We now have that becoming A star. So A star union A star using rule 9 again. A star star is this, using rule 10 is the same as A star. But now we have A plus cannot be equal to A star. So those two are not equivalent. So here we've shown that they are not equivalent rather than that they are equivalent. And maybe you could have seen that looking at this up front and said, well, this is star. This whole thing is star, so that has to include a lambda. This A plus here cannot include a lambda. So maybe you could see that up here, but in this case, we've now built it down where A plus cannot be equal to A star. And we could, how do we know that? Well, we could write out the definitions of plus and star, and notice one is the union from of the language concatenated with itself from 1 to infinity, the other one is 0 to infinity. So 0 includes the lambda, 1 does not. So if we subtract those, if two things are equal, when we subtract one from the other, or the second from the first, we'll always get the empty set. In this case, we'll get a set containing just lambda. So therefore, they are not equivalent. So we can prove that they are not equal, just like we could prove that they are equal. Now, that proof that they're not equivalent there is going to be, or that model of how we prove that, either to prove something true or prove something false, we're going to use here in a little bit. But one thing before we get to that is notice you could abstract, notice these ones back here, these are with specific regular expressions. A plus, A star, union A plus, that whole thing, union lambda, the whole thing, star. Those are specific regular expressions. But notice we can also use that process of manipulating things using kind of abstract expressions. So here we say we have R, S, union R concatenated with T, union S, union with RT. That is always going to be equal to RST, no matter what regular language or what expression we have plugged into R, S, and T. And that kind of ability to abstract completely new rules, like we could make this a new rule in our table if we can prove that this is true. And we could prove that that's true because notice this union that, we could essentially reorder these so that we have RS union RT union RTS. We could then distribute the R across this and get RT and RS, and then we would have we could organize those again to get RS union RS, which is just RS, union RT, and get RT. So now we have RS and RT, and we could factor out the R and get the same thing on this side. So this is something that we could prove by manipulating this or expanding this to get that, as long as we justify each step. And we know that no matter what languages I plug in for these, as long as they're a regular language that's definable by a regular expression, we know this will always hold true. So that kind of ability to prove something about a whole class of things or something more abstract is really powerful. And that's called a direct proof. Sometimes it's called a deductive proof, but the idea there is the same, that we're justifying our steps that we're taking one at a time, going through this chain of steps to get to something that we want to get to. So looking at direct proof, which we'll do in a second, or any kind of proof for that matter, they're kind of two extreme views. And we talked about this a little bit on the first day of class. And automata classes, formal languages classes have typically have a good number of proofs in there. And we're going to do a little bit of that in here. But before we do that, I want to talk about two of the extreme views. There's kind of these computer science extremists that say or believe that every program that you ever write and every algorithm that you create requires some formal proof of correctness and completeness, meaning that if you just write a program and run it, it doesn't mean anything, even if it works when you test it, that you need to have a formal proof of correctness and completeness for that particular thing to have that be considered correct. And then on the other end of the spectrum, there are these kind of hacker/programmer extremists that have disdain for the theory and for proving things. It's like, why would I prove anything when I could just write a program and run it and see if it works? And really, from my point of view, neither of those is a good or a healthy attitude. That really what it makes sense to have is this balance between the two, that we want to essentially use proof where necessary or where it makes sense as a tool, and not spend your time proving things that don't need to be proved. So in other words, rather than saying I'm going to do it for everything I create, I'm going to use it as a tool for certain things that I create where it might be difficult to know if they're correct. And one of the reasons for that is that you can't usually test for every possible input. So as an example of that, think about, let's say you're writing a compiler. How many possible programs are there that you could write that you would feed into a compiler? Well, for a compiler to be considered correct, it has to compile every possible program you could ever write. And there's an infinite number of those. So you can't test with every possible program that anyone would ever write. It's impossible. Secondarily, it has to reject or produce errors on every possible program that's wrong. And there's an infinite number of those as well. And so we can't really test every possible bad input or every possible good input because there is an infinite number. So the idea is it would be nice to know when that your program is correct. It'll work correctly for every program you put in. It'll reject all the ones and not produce code for all the ones that are broken. And so the idea there, it's important to have some sort of proof or theoretical underpinning for how you make that compiler rather than trying to hack something together and just trying it and see what it does. Now, proofs can also help with if something fails to know why that thing failed. And so, again, we're going to use proofs in this class as a tool for doing that stuff. And I think that's the healthy way to look at this. Don't view it as everything needs a proof. Don't look at it as nothing needs a proof. Look at it as a proof as a tool, especially when we're dealing with a class of things, like a large class of algorithms or a large class of problems, rather than having to solve the same problem over and over again or make sure that it works on this case, in this case, in this case, in this case. It's easier to prove it for the entire class, and then you know that methodology will work for all of the things in that. And you can also learn where the boundaries are of that. So proof can point out this can work for this class of thing. It won't work for these other ones. So it's a really powerful tool. And looking at an example here. So let's say here's a problem like we had earlier. We want to say, is this equivalent to that? And if we use the hacker approach and we just say, well, let's test some input strings. Let's take some strings from this and see if we can get them from that. So we might take some strings from the left-hand side and see if they are in the language from the right-hand side. So we say left-hand side, okay, I can get an A. Well, yeah, I can get an A over here. Well, I could get an AA. Yeah, I could get that over here. I could get AAA. I could get that over here. So the assumption that a programmer / hacker mentality might make is, well, I tried a bunch of these and they all showed up over here, so it's probably the same. But notice that that assumption of those being the same because I tried some finite number of test inputs and they all seemed to work could be misleading, could be wrong. And in fact, in this case, it is wrong. They're not equivalent at all. So let's look at why. So why are they not equivalent? Well, let's use a form of direct proof to do that. So it's kind of like we did earlier. We start with the left-hand side and the right-hand side. We're going to then take this star and expand it to A plus or lambda. We have a rule for that. And I'm going to leave off the rule numbers here for this example. But there's a rule for that. And then from that point on, we're now going to take the A plus and those things in parentheses, and we're just going to move the parentheses over, which there's a rule for that. So in other words, we're going to associate these differently. We're going to use that associative property of union, and we're going to put the plus with the plus and leave the lambda outside. So we move that over. And now we have A plus union A plus. Anything union with itself is itself. So now we're just down to A plus. And then A plus or lambda is the same as star, and AA star is the same as A plus. So now we have A plus on the left-hand side, A star on the right-hand side, and those cannot be equal. So those are definitively not equivalent. And where the hacker test of just trying some input missed or misled us and led us to believe that they were the same, now through this, using more of this kind of procedural process of manipulating one to try to get it to match the other has shown that those things cannot be the same because this one has lambda, this one does not. Now, maybe you could have seen that up here looking at that, but in this case, we know for certain it's really easy to now see this is not the same as that. Where the hacker test we did back a little bit ago, we didn't necessarily know that because we tried some inputs and they all seemed to work. All right, so the general concept of direct proof works like this. We start with some initial statement, and then that initial statement leads us to some first kind of implication, which leads us to another implication, and so forth, all the way up until we get to our goal statement, which is the thing we're trying to prove. So in this case, to abstract that, we have P as our hypothesis, which you could say H here. And over here, we have Q as our conclusion, which you could put a C. So from hypothesis to conclusion, and we go through some sequence of these deductive steps. Now, in other words, this arrow is kind of implies. So P, you tie that together with some reasoning that says P has to mean that P1 is true, which has to mean or imply that P2 is true, which implies P3 is true, which implies, and that continues for as many steps as you need to eventually get to implying that Q, our conclusion, must be true. And the way that we read that is we say that as long as each of these steps is fully justified, then the way to think about that is that if P is true, then that implies Q. Or another way to think of that is Q is deduced from P. And that process there, we're going to apply to a proof that's not really automata based right now. So let's go ahead and go through this proof. And we might say if two integers are multiplied together, the result will always be an even integer. So we have two even numbers, we multiply them together. Is the result always even? And we could start with kind of like that hacker / programmer mentality and say, well, let's just try a few. 2 times 2, 4. Yeah, it worked there. 2 times 3, 6. Yeah, that's even. How about 10 times 12? 120, that worked. But notice that there's an infinite number of even numbers. And what if there's one that doesn't work? Or maybe there's two of them that we pick that just for whatever reason mathematically don't produce an even number. And so that test, we could never test all of them because it's an infinite number, but let's try to prove this with a deductive proof. All right, so to start with, let's look at what our given is, or our hypothesis. The given statements are kind of where the hypothesis starts. That we're going to say the set of even numbers we're defining as x, such that x is 2n, where n is an element of z. And this capital Z like this is usually like a special z. For whatever reason, the font on this don't allow me to choose that, but it's a special Z with like a double kind of slanted line, more vertical line. But that is saying that the set of even numbers is all numbers such that that number is 2n, where n is an integer. So in other words, we take 2 times an integer, that always results in an even number. And that makes sense because all even numbers are multiples of 2. They're divisible by 2. All right, so in other words, we have our two even numbers. Z1, that's an integer, an even integer. Z2 is an even integer. And so if we multiply them together, we're saying this is our conclusion, our goal, is to find as if this multiplied by that, an element of the set of even numbers. And we're claiming that it is. Now, how are we going to prove that? Well, to start with looking at how we're going to prove that, let's start with this. So if we have this even number Z1, we know it's even if we can write it in the form 2n for some integer n. So Z1 equal 2n. That's by our definition up here of what an even number is. In other words, that if z is an even number, then it's a multiple of something multiplied by 2. Some integer multiplied by 2. And the same thing for Z2. It's also even. So that means that we can say it's 2 times something. It's m instead of n, because it's a different number than that one potentially, but it has to be an integer. So now we have those two, Z1 and Z2, defined as 2n and 2m. So we can kind of define those, and then now we have Z1 times Z2. We could substitute the 2n in for Z1, the 2m in for Z2, and then we want to find out, does that result in an even number? When I take this sum, and notice it's not a specific even number, this is just any even number multiplied by some other even number, does that result in an even number? All right, so let's go through the deductive steps here. So does Z1 times Z2 result in an even number? Well, let's do substitution for the 2n and 2m, which on the previous page, remember, we defined those here. Those are equivalent. So we're just substituting those in for Z1 and Z2, and we get 2n times 2m. Does that result in an even number? And we multiply that out, we get 4nm. Does that result in an even number? Well, let's factor out a 2 and say that 4nm is the same as 2 times 2nm. Does that result in an even number? And you'll notice now we have that 2 times 2nm. Well, we could say that's the same as 2k, where k is 2nm. So it's 2 times something, which is the definition of an even number, as long as 2nm is an integer, which it is. So therefore, 2k has to be an even number. So no matter what numbers we plug in here, we're always going to get an even number out of that. So the chain of that proof goes like this. Start out with Z1 and Z2. By definition of what makes, and we know those are even, so by definition of even numbers, there's some number multiplied by 2 for each of those. We multiply those together, we get that. We factor out the 2, we get this. And that's 2k, where k is 2nm. And that, therefore, the result has to be an even number. And so that proves that any even number multiplied by any other even number is always going to result in an even number. And notice we did all of that. We could do all of that without having to resort to testing any examples at all. We don't have to, for example, try some input and see what happens. It's just right there in the proof. And we justified each step along the way, meaning that any even number times any even number is always going to result in some even number. And we know that 100% of the time, and in all cases without ever testing a thing because of this proof. Now, let's do another one. What about odd numbers? Is an odd number multiplied by an odd number always an odd result? And that might be a little less intuitive. So you have an odd number and an odd number. Does it always give you an odd number? Are there cases where it doesn't? Well, 1 times 3 is 3. So yeah, that worked there. What about 3 times 3? 3 times 3 is 9. Seemed to work there. But notice this one's a little less intuitive than the other one. So let's try to prove it. Can we prove it to be true? Or if not, can we prove it to be false in some way? And so to go about proving that, what I want to do here is talk about or think about, well, what does it mean for a number to be odd? And as part of that proof, we're going to say, well, an integer is odd if it's an even number, 2n plus 1 more. So in other words, odd numbers are just shifted by 1 from even numbers. We could have done minus 1 here, but we're just going to do plus 1 there. So in other words, we take an even number, we add 1, we get an odd number. All right, so we've defined that. And now, just like we did before, we're going to do those substitutions. So we have 2 odd numbers, z1 and z2. We can define z1 as 2n plus 1, z2 is 2m plus 1. We can do those because this is an odd number, and we had all odd numbers can be written in a form that looks like this. And then we have the z2 is also an odd number. So now we're going to substitute them in for z1 times z2. And does that result in an odd number? Well, let's go through and do that. So substitute those two things from here into there. And we get 2n plus 1 for z1, 2m plus 1 for z2. Now let's go ahead and multiply that out on the left-hand side there. And now we get, again, using the FOIL method, the first 2n times 2m is 4nm. And then 2n times 1 is 2n. 1 times 2m is 2m. And then 1 times 1 is 1. So it's they call it the FOIL method, first, outside, inside, last. You're probably used to that from algebra. So we just multiply that whole thing out. We get 2nm plus 2n plus 2m plus 1. And continuing on, we now factor a 2 out of this first part of this. So we factor a 2 out, and that gives us 2 times 2nm plus 2 plus m. Does that result in an odd number? But notice now we have this form. This is 2 times some integer plus 1, which is the format for an odd number. So we say that's the same as 2k plus 1, where k is equal to the stuff that was in parentheses here. And we now know that has to be odd. And notice that I know that has to be odd without doing any testing whatsoever. So an even number times an even number will always produce an even number. An odd number times an odd number will always produce an odd number. And again, the chain for this one goes like this. z1 times z2 is the same as 2n plus 1 times 2m plus 1 is the same as all of that multiplied out. Factor the a2 out of this to get 2 times 2nm plus n plus m plus 1. And that's the same as 2k, where k is the stuff in parentheses here, plus 1. And that fits the definition of what an odd number looks like. 2 times some integer plus 1 more. In other words, an even number, and we shift over by 1. So that has to be an odd number. So now we've proved that an odd number multiplied by an odd number is an odd number, always, without trying anything. And that's a pretty powerful thing. Even though these are simple examples related to math, that's a powerful thing that we've just proved there. Because we've proved something about an infinite size set of all numbers, all integers, both even and even results in an even, odd and odd results in an odd. We know that for all of them through this simple deductive proof we did, the direct proof we just did. All right, so to kind of summarize here what we're talking about, and that is we start with our hypothesis statement or our given. We want to work towards the conclusion statement, what we're trying to prove, and we need to justify each step. And when we say justify each step, that means that we have to have some legitimate argument or manipulation to get us from the previous one to the next one. So for example, back here, we had a logic that said because odd numbers look like this, and we're given that that's an odd, we can substitute that in. And this is also an odd number, so we can substitute that in. And so taking this, using algebra, we can get that. Using some more algebra, we can get that. And then that fits the form of an odd number. So therefore, as Peter notes, we have to justify each step. In other words, you can't get to a part of the step and just say something like, well, Paul told us in class this was true, so I'm going to stick it here in my proof. Or you can't use something like, this feels right, so I'm going to stick it in here as this step. You can't do that. It has to be a legitimate justification. You also can't say, I saw on the internet somebody said this, so it's true. So in other words, we have to have some legitimate justification for every one of the steps in that proof. And it's like a chain, that if there's one step that is flawed or not well justified, then the whole chain falls apart. It's not a proof anymore. So we have to have some legitimate justification for every one of those steps. Now, notice we can use that same general process to prove things about general or abstract things about languages and automata, and we're going to do some of that this semester. But that's all I wanted to get through today. Is kind of a brief introduction to that, but I want to leave you with a couple questions. What about an even number times an odd number? Does that always result in an even? Or does that always result in an odd? Or does it sometimes give one and sometimes give the other? And so I'll leave that up to you to kind of go through that, the proof steps, kind of like we had over here. But think about that. What if this one's even and that one's odd? Or that one's odd and that one's even? What do we get? Even or odd? Or maybe sometimes one, sometimes the other. So can you prove that? So that's pretty much it for today. What I want you to do is finish the lab and then look out for a quiz. The quiz, when it gets posted, is going to be doing one of those manipulations, or maybe a couple of manipulations of regular expressions to prove that they are either equivalent or not equivalent. So look out for that. That should be posted to the course page today. Finish up lab 1 because I want to go over that next class, and if you're late and you turn it in after I've gone over it, then you won't get credit for it. So make sure to finish up lab 1 and watch for a quiz. And next class, we're going to dig a little bit farther into some stuff related to proofs, and then we're going to cycle back into talking more about some things with formal languages and automata. And we're going to use that kind of direct proof concept later on the semester. We're also going to look at some other types of proof coming up here. And one of the things that I want to point out is this class is not going to be real proof heavy like some automata classes are. We're going to use it as a tool when it makes sense to, and we're going to spend a little more time looking at the automata still at a theoretical or abstract level, but we're going to have an eye towards applications for it this semester as well. All right, let's go and stop there. Everybody stay safe, wash your hands, and next class we'll continue on where we left off, but watch for that quiz and try to finish up that lab. And that's it for today.